Okay guys, now in the last video we have studied the colligative property. Let's continue that in this video. Okay, so we were using the Rolle's law, if you remember that. So let's do some problems related to Rolle's law. Okay, so let's use that. Okay, for example, our question is, what is the vapor pressure of a solution made by adding 10 ml of the glycerol to the 50 ml of the water at 50 degrees centigrade. Okay, that's the question. So there is another part of this problem is calculate the vapor pressure lowering delta P at this temperature. The vapor pressure of the pure water is this. You know, vapor pressure get lowered if you add the solute on that. So density is given, molar mass of the glycerol is given, okay, and the molar mass of water is, yes, of course it is 18. So we know that. So now let's do this problem. Okay, so first of all, the glycerol, which is C3H8O3, is formalized. So its mass is equal to, first of all, find out its mass, right? C3H8 mass equals to density times the volume. If you see that, density times volume. Okay, so mass is density times volume, and this is equal to 12.6 gram, the mass. Now convert that into mole. You know that to use the Rolle's law we need the mole. That's why we converted that into the mole, and that is we divided just by the molar mass, that is 0.137. So mole of that. Now let's find the mole of water also. 500 ml is, this is the density. We multiply with the density, convert that ml into the gram, convert that gram into the mole, and that is 27.4. So the mole of glycerol, which is C3H8O3, is equals to 0.137, right? So that much mole. So mole of glycerol is equals to. Similarly, now let's see the mole of water. So mole of water is equals to that is equals to 27.4 mole. Okay, so now you know that the Rolle's law, mole fraction, you need the mole fraction. So mole fraction of water, that is denoted by chi water, right? That is equals to mole of water, mole H2O. So mole is, let's say, denote that by N, right? N H2O. M is the molality. Small m is reserved for molality. Capital M for molarity. Okay. Na is for the Avogadro number. And N is for the mole. Okay. You can give any number, any letter, guys. Okay, but that is reserved for mole. So NH2O divided by N of H2O water plus glycerol, right? N of the glycerol, C3H8O3. So if you do that, plug in this everything value here, right? The glycerol mole is this, water mole is this. That's why if you plug in that, you have the mole of water, the mole fraction of water will be equals to 0.995. We plug in everything. Okay, that is NH2 is how much? 27.4 divided by 27.4 plus 0.137, and that is equal to this. So if the mole fraction of water, then mole fraction of the glycerol, okay, C3H8O3, that is equals to 1 minus this, right? 1 minus 0.995, that is equals to 0.005. Because it is the binary, that's why 1 minus. Okay, if there are mixture of 3, then you have to calculate other also using same. If you use the formula, if you want to use the formula, then what you can do is C3H8O3 is equals to N of C3H8O3 divided by this, and that is the same number, you will get that. So you find the mole of this. So what is the pressure then? According to the Rolle's law, what is the pressure? Pressure is equals to P, pressure solvent, is equals to mole fraction of solvent in water, times P naught of water. That is the pressure of the solvent after adding. Okay. So yes, that is equals to, you just plug in that and you will value mole fraction of the 0.995 times the P naught is given, right? Is that the P naught given? So okay, that is now, and yeah, the 92.65. That is the P solvent. Okay. So, but the vapor lowering delta P is different. Delta P is equals to what? Instead of solvent, you have to solute, right? So X solute is with a C3H8O2 times P naught of water. That is the formula for the lowering, vapor pressure lowering. That is, it is given 0.005 times 92.65. That is equals to 0.461 torr. That much torr the vapor pressure get lowered if you add the glycerol. It's not that much, right? But the 1 atmosphere is your atmospheric pressure. Half of that atmospheric pressure is lowered, means it's a significant, right? It's a significant. But the vapor pressure of the solvent is this. Vapor pressure of the solvent is 0.995. Here is, you see, here is little bit, we have to give that number up. Okay, it's a typo is here, guys. Okay, now let me add that here. So that is here, right? So 0.995 is your X water times 92.65 is your torr, because the PS2 not is given that much torr. See, this is given here. That's why we plug in that also here, 92.65. So that's the vapor pressure lowering done. So we have calculated both. It's easy, right? Vapor pressure lowering is vapor pressure lowering formula is what? Delta P is equals to X solute, mole fraction of solute, times, what is the times? Pressure P naught. That is the delta P. So you see, so if the mole fraction of the solute is large, your pressure decreases by a loss of amount. It's changed that much. Yes, of course, right? More solute, more pressure decreased. So vapor pressure get decreased, right? Solvent can escape easily, but if you add something additional, then that additional also can attract the solvent molecule. That's why it's difficult. So this is here, right? And then now let's see that boiling point elevation. This is, right, this formula already we have discussed about. Delta TB is equals to delta T boiling point elevation equals to KB times M, and a freezing point depression equal to delta TF, that is freezing point depression, that is equal to KF times M. But if remember that if this is the ionic compound, then what we see that we use the Bond-Off factor also. Then if ionic compound, ionic compound means if you put that in the water, it can dissociate, right? If it can dissociate, then at that time we use the Bond-Off factor also. For example, delta TF will be equal to I KFM, and delta TB is equal to I KBM. That will be the, if that is ionic. And the Bond-Off factor is approximately equal to the number of ions. For example, NaCl, right? It can give you two types of the ions. One is sodium plus other is what? Chlorine minus. That's why Bond-Off factor I is equal to 2 for NaCl. This is pretty easy, right? So for example, MgCl2, let's say, okay, it has what? Mg plus 2Cl, right? That's why it has a 3. It will have 3. So like that, okay, if they are ionic, if they can dissociate, then Bond-Off factor is total. This is a Bond-Off factor I is equals to 3. 1 is Mg and 2 are Cl. So 1 plus 2 equals to 3. So that we just put that if it is an ionic compound, then we will put just that I in beyond I as a factor, right? So delta TF for ionic I KFM. This is the Bond-Off factor. So you have to multiply that. It means that as much as the number of the particle increases, right, that much the vapor pressure get lowered. Similarly, that one temperature get freezing point get decreased, and that much boiling point get increased. It means that sodium chloride, right? It has a 2. That's why it has a double capacity than another similar non-ionic compound, right? For example, NaCl has also, suppose, I am saying suppose, NaCl has also Kf is equals to 1.8 degrees centigrade, means that it can decrease by 1.8 degrees centigrade. With the molality, per molality, okay, per molality, and the another compound X has also Kf is equals to 1.8. Kf both has the same, right? But the NaCl is ionic, X is not ionic. Then NaCl delta Tf is equals to I times Kf times the molality. Suppose the molality is also same. Suppose the same molality, and then sodium has, suppose the molality equal to 1, sodium molality equal to 1, and X has also molality equal to 1, then I is sodium chloride, I is what? 2 times Kf is what? 1.6, 1.8 degrees centigrade, right? Because the molality will cancel, okay? Because it's per molality and times. Okay, so yes, we have the this delta Tf, right? We have studied that. Now let's go to the another sample problem. So boiling point and freezing point of a solution, we will find that the new, right? You ate 1.25 kg of ethylene glycol and that freeze to the 4450 gram of water in your car radiator. What are the boiling and freezing point? So let's do that. First of all, convert that into the mole, right? The molality. See that we convert that into molality. This much molality. So everything mass of this is we divide by that, and this is the mole, and the molality is mole per kg, right? So this much kg of solvent. So that's why this is your molality. Now, and if you know the molality, then what is the delta Tb is equals to molality times Kf, right? Molality times Kf, because the glycol is non-ionic, right? It's the organic compound. That's why non-ionic. That's why point of factor is just 1. So this much is delta Tb. Okay. Then what will be the solution? Solution is always delta Tb is positive. That's why 100 degrees water plus 2.3. That is 102.32. Easy, right? And what will be the freezing? Freezing point diffraction constant times the molality. That's 8.41. Freezing point always decreases, right? That's why 0 degree is what your freezing point of the water, which is solvent, minus delta Tf. 0 minus this minus 8.41. Done? Okay. Now let's go to the next. Let's study the atmospheric pressure. So sorry, the osmotic pressure. So let's understand the osmotic pressure and how does it work. Okay, osmosis is the movement of solvent particle from a region of lower concentration to a region of the higher concentration. So what happens is through a semi-permeable membrane. Suppose that this is one, you have a container and you separate this container by a membrane here. There is no water leak, and this is your container, right? Let's see, this is your container, and that is your container. Basically, let's say this is your big beaker, suppose. Okay, so now you have here, this is your semi-permeable membrane in between. Semi-permeable membrane means it's not permeable, it has very fine pores. Okay, it is a porous material. So now you put that here, and now there is no leak, nothing get leak from here to here. Okay, so you have very nice leak tight, you make that. And now let's put that here, the solvent is here, just the water, and here you put the sodium chloride water, sodium chloride plus water. Now let's say this is okay. Now to distinguish sodium chloride and water, let me put the sodium chloride as a blue color. So in this left hand side you have a sodium chloride and water. Sodium chloride is blue and water is this. So what is happening? The region of the higher concentration, the movement of the solvent particles from a region of lower concentration to a region of higher concentration. Look at that. Here, what is the concentration of sodium chloride? Concentration sodium chloride is equals to NaCl is equals to 0, right? No sodium chloride here. Here is, for example, molarity equal to 0.1. Let's see that. Here you have a sodium chloride, but it don't have, right? So the solvent will move from lower concentration to higher concentration because of the attraction, and through the semi-permeable membrane, it has the pores and the water will pass through that, and from lower concentration to higher concentration. Here the concentration is 0, okay, but this is the water. Here is sodium chloride water, that's why water can move, but this is the pure water, right, in case of the solvent. But if you have a concentration also, then also can move. In that situation also can move. For example, this is your beaker and you have a semi-permeable membrane here. You separated this beaker by 2, okay. Let's say, let me put that is this one. See, now it makes more sense, right? This is the semi-permeable membrane here, and at this compartment you have 1 m solution, 1 m NaCl, 1 mole per liter of sodium chloride. This is the concentration in this side, and this side is, for example, the same sodium chloride, but here you have a 2 m NaCl, molarity is 2. So it has a low concentration, it has a high concentration, right? At that situation, water, not the electrolyte, water will move from here to here, okay, until both should have same concentration. It will move from here to here until both should have same concentration. It means that it is in the equilibrium. So that is said to be, and then, so that is the osmosis process. That's the process, osmosis process. Movement is the movement process of the movement of the solvent from low concentration to high concentration. Okay. Or solvent will always flow from a more dilute solution to a more concentrated, right? That more dilute to more, that is the osmosis process. So what is the osmotic pressure means? This is the pressure that must be applied to prevent the net flow of the solvent. What is the pressure? Right? It will stop to flow, and what the pressure at which it stops to flow, that is the osmotic pressure. Is the pressure that must be applied to prevent the net flow. So we can apply the pressure, right, to stop that net flow. So that how much is the pressure we have to apply to stop that net flow, that is said to be the osmotic pressure, and its formula is even here. Osmotic pressure is equals to mRT. Remember that in previous 2 cases, molality, not the molarity. Previous 2 cases, molality. In this case, this is molarity, okay. In the osmotic pressure pi, or the capital P, is equals to molarity times gas constant times temperature. So look at that, the osmotic pressure depends upon temperature, right? Molarity is constant thing, or you can say that the molality also, it may change. So R is the gas constant, T is the temperature. So if the molality is fixed, then the osmotic pressure depends upon the temperature. Higher is the temperature, you see, high atmospheric, high osmotic pressure. Low is the temperature, low is osmotic pressure. That's fine. Okay. So that is the osmotic pressure. Now let's find the molar mass from some osmotic pressure. This is a problem. A biochemist have discovered more than 400 mutant varieties of the hemoglobin, the blood protein that carries O2. That's the hemoglobin, right? So a physician dissolved 21.5 milligram of one variety in water to make 1.5 ml of the solution at 5 degrees centigrade. C measured in osmotic pressure is 3.61 torr. What is the molar mass? That's easy, right? What is the osmotic pressure is equals to molar mass, right? Let's see that, molar mass times R times T. Plug in everything here. So the what will be the molar mass is equals to osmotic pressure, right? Osmotic pressure, this molar mass, this is equals to this, you have to divide, right? So RT, right? So molar mass equals to osmotic pressure by RT. We just did, this is your molarity is equals to this, right? Oh yeah, molarity. So molarity is equals to, we find out 2.08 times 10 to the power minus 4 molar. So the molarity times R times T, right? That's why molarity we can, now if you find the molarity means a mole per liter, right? So the mole per liter. So the mole per liter is, that is 2.08 times 10 to the power minus 4 mole by 1 liter of the solution. Okay, so how many liter of the solution? So see, this much ml, right? See that here, convert that ml into the liter, and that is 0.0015 liter, right? Times 0.0015 liter, and that is equal to liter cancel. You see that liter cancel, right? And then that is equals to, and it is, if you calculate that is equals to 3.12 times 10 to the power minus 7 mole. So if your osmotic pressure is given, if you can have the osmotic pressure, you can measure the molality guy. Okay, whether the temperature is given, temperature is 5 degrees centigrade. How wonderful, right? So the molar mass you can calculate by this colligative property are very good property, right? They are very important. You can measure the molar mass of any substance. So that is the molarity. If you know the molarity, and then quickly you can guess the molar mass also, because you have the molar mass. Okay. So now, so another is, yeah, Bontoff factor we already have discussed. You see that Bontoff factor is here. Measure the value for electrolyte solution by expected value for a non-electrolyte solution. That is actually Bontoff factor, but just let's skip it. Okay, Bontoff factor is, I already explained. So that's why for the electrolyte or the ionic solution electrolyte, you have this. We have to multiply the Bontoff factor also. Now how do we calculate the Bontoff factor? We already have discussed, right? Two type of ion, Bontoff factor 2, three type of ion, Bontoff factor 3, and like that. So here is a sample problem. So the problem says that depicting strong electrolyte solution. Okay, which one is the strong electrolyte solution? That we have to see that here. Problem: 0.952 gram of the magnesium chloride dissolved in 100 gram of water in a glass. Okay, now let's see this problem. 0.952 gram sample of magnesium chloride dissolved in 100 gram of water. So which scene depicts the solution? First of all, there are 3 scenes. You can label the solution A, B, C, and B is what is the amount mole represented by each green sphere. So that's also easy. Assuming the solution is ideal, what is the freezing point is much. So okay, now let's see that here. Solution B contains this much gram of MgCl2 in 100 gram. That's why this is your mole, gram. That's much your mole, right? Every 1 mole of MgCl2 produces the 2 mole of chlorine, right? MgCl2 has 2 mole of chlorine. That's why you can see that here. So mole per sphere is equals to 2.5 10 to the power minus 3 mole per sphere. So there are 8 green sphere. So every 1 mole of this 2 mole. So there will be 0.2 mole of chlorine. Okay. So if you see the solution C, assume an ideal solution I equal to 3 MgCl2 because there are 3 ions per formula unit, right? So you see, right? Which scene depicts the solution best? So magnesium chloride means 2 chlorine for 1 magnesium. Which has that? 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8. Right? So which is the amount of mole represented by each green? So we have done that now. So that's why this is. Now solution C. C says that assuming the solution is ideal, what is the freezing point 818 atmosphere? Now to find the delta TF, right? Molarity. So is mole per liter. This is the mole, right? And delta TF is equals to I molality times this. So that's the molality. So because we have calculated the molality here, we converted that into kg. That's your TF is what? 0 minus this, because the what? 0 minus this is minus 0.55. It's the same as like previous question. Now osmosis pressure, we are studying the osmosis pressure. This is one example osmosis pressure. You see that pure water, sugar solution, this is the semi-permeable membrane, which is the pure water is outside, the sugar solution in. What will happen? Water will go in and it will be swollen because the solvent moves in. So this is one example. So in the osmosis pressure, we studied what is the osmosis pressure, and previously already you have studied, no need to repeat that. But what is the semi-permeable membrane is important, right? A membrane with tiny pore, I already say that it's the porous material that are big enough to allow solvent molecules to pass. That is the semi-permeable membrane. So osmotic pressure, we already studied that, the pressure necessary to prevent the osmosis. How much pressure you have to apply to stop that osmosis process, that is osmotic process. Okay, osmol, the molarity multiplied by the number of particles, that is the osmol that we used in the terminology in the osmosis pressure. So now let's see, again this is the problem, 0.89% weight by volume. Now we have studied, remember that weight by volume, volume by volume, these lots of things. Sodium chloride solution is referred to as the physiological saline solution. What is the osmolarity? Osmol. Weight by volume is this much gram in 1 liter of the solution, right? So this much gram times this is the mole, right? We have divided mole by liter, that's the osmolarity, right? That's the molarity. So mole per liter, right? So because each mole of sodium chloride dissolved in the water dissociates into the sodium and the chlorine ion, the osmolarity of the solution is 0.15 times 2, because this is your mole, the molarity times the how many particles? 2, that is 0.3. Done? Now related to osmosis, there are some more other terminologies. So isotonic solution. So that is the solution with the same osmolarity. That's the isotonic. If two solutions have same osmolarity, they are isotonic. So, and the hypotonic means a solution with the lower osmolarity. One is less osmolarity, other has more osmolarity. That is the hypotonic, is the less. Okay. So that is the blood plasma basically. So the higher is the blood plasma. So lower osmolarity than the blood plasma and the red blood cells. That is the hypotonic. So you know that you will require these terminologies. Basically, they are useful in the if you are going to the medical field, right? And the hemolysis, the swollen and the bursting of the red blood cell because they cannot resist the increase in the osmotic pressure. That is said to the hemolysis. So hypertonic, yes, of course, hypotonic is less, hypertonic is more. Hyper means always more, hypo means always less. Okay. So that's about the osmosis. So if you think about the hemodialysis, right, this is the process of hemodialysis, blood out, here blood in, right, here is the membrane, so dialysate out comes from, here is the dialysate in, you send the dialysate liquid from here, it flow from here, and this is a jacket, and you have the blood in from these membrane tube, these are the tubes, it go and blood in from here, out from here, and dilate out, and you have the capillary dialyzer is like that. Okay, so we have already studied the osmotic pressure, right? So now this is also the repeat, just we did that previously, this problem. Okay, so the Electrolytes also we have already studied that. Colligative property, these are just the repeat of the previous. So now, so let's see the this also, right? Now the viscosity. So viscosity, osmosis, colligative property, viscosity. Okay, what is the viscosity? Viscosity is the resistance of the fluid flow. That is the viscosity, and it results from the intermolecular attraction that impedes the movement of the molecules around and past each other. So the stronger the intermolecular force, the higher the viscosity. The viscosity decreases with increasing in temperature. Yes, of course, because the temperature increases the kinetic energy, it increases the intermolecular distance. Because of the intermolecular distance increases, the attractional force decreases, right? Because the force is inversely proportional to the distance. So if two particles are close enough, they have more intermolecular force of attraction. Because the temperature makes them apart from each other, means that increases the intermolecular distance. So that's why viscosity also get decreased. And the viscosity is affected by the molecular shape also. You know the shape, the hydrogen bonding, in case of the hydrogen bonding also, and the van der Waals dispersion force also, right? More contact surface area, more is the dispersion force, right? So we have studied that thing same in the intermolecular force also. That's why similar here also, viscosity is affected by the molecular shape. Among liquids with the same type of the intermolecular forces, those that consist of the longer molecules having the higher viscosity, right? Longer molecules have the more contact surface area. That's the reason you have a more intermolecular force. That's why it has more viscosity. So some viscosity at temperature and water, viscosity of the water at temperature are given here. You see that. So you see, temperature increases, viscosity get decreases. That's because the kinetic energy increases. Kinetic energy increases means that the intermolecular force get decreases, right? So because of they are more apart and they pass from each other faster. That's why less effective intermolecular force. So temperature increases, the viscosity get decreases. You can see that here. So that's it. We have finished chapter 6. Okay, we have finished this. So chapter 6, colligative property, very important property. We have studied and we have studied the viscosity also, and that's it for today. And we have the osmosis also. So and hemodialysis, viscosity, and let's see that capillarity. We haven't studied the capillarity, so let's study this capillarity also. So capillarity is the rising of the liquid through a narrow space against the pull of the gravity. That's the capillarity. Now let's discuss the capillarity little bit more. Okay, so capillarity is if you have a narrow tube is here, smooth narrow tube here. This is a narrow tube. Okay guys, wide tube is capillarity. Your tube should be capillary, right? Yeah, the big cylinder, for example, you don't think that there will be the rise. It should be narrow. Okay, narrow space against the pull. Now, this is the liquid filled off in here. Suppose the water. Oh, okay. So gravity will pull this down, and because the capillarity effect, some liquid pulled up, and that is that pulling up of the liquid against the gravity is the capillarity. So capillarity is because of the competition between intermolecular forces within liquid, cohesive force, and those between the liquid and the tube wall, adhesive force. There are two types of the force. Now let me zoom up that capillary. Now let me zoom up that capillary. This is the capillary. Okay, this is very narrow tube. Okay, guys, I am zooming up. So now one force is here. See. This is water molecule, this is another water molecule, this is another, this is another, these are water molecules. See that? That's a liquid, any liquid, and let's say water molecule. Water is very good example. It has nice capillary reaction. So what happens is, there are two types of the forces, you can see that. One force is this molecule. So one water molecule can pull another water molecule. See, this water molecule pulled by this. This also can pull by this, this also can pull by this, this also can pull, right, and this also can pull this also. means that the water between water, the force between water and water, means liquid and liquid. If your liquid is H2O, H2O, this is one force. So other force is this wall has also molecule, right? For example, the tube means silicon dioxide, suppose that. It is made up of the silicon dioxide, suppose that. This is the wall, glass. And glass wall has also the molecules, right? So let's say, let me make the glass wall by this, okay guys? These are the glass wall molecule, okay? So let me microscopic way. So I am showing this, the molecule silicon dioxide at the wall. See here. These are the glass molecules. Okay. And what happens is, these water molecules also can be pulled by, there is another force which is the force between the, so that's the force between the, let me take the force between the, this water and the glass. This is also the attractional force, right? See, this is also attractional force. So that's why some water molecule pulled up by this glass. What happens is, this glass attract this water molecule, this glass molecule attracts this water molecule, these glass molecules attract this water molecule, and other water molecules pulled down. So this don't have any attraction from glass to this water, this don't, but this corner molecule can be attracted by glass molecule. So whatever the wall of capillary, whatever the force between wall and capillary to the water or the liquid is said to be the, what is that? That is said to be the adhesive force. Attaching, how much force this get adhesed there, means attach there, adhesive force. And the water and water is cohesive force, within the liquid, and that the cohesive force, right? So there is a competition between adhesive force and the cohesive force. It means that if adhesive force is this force between wall and this molecule is larger than the force between this water pulls down, then what will happen? This force will win, right? The force between wall and the water will win. So whatever the molecule that is attracting by the wall will attach with the wall, and other will go down. So whatever the molecules are attracted by the wall will be attached with the wall, and other molecule will go down. So there will be little bit rise of the meniscus. So that's why if you see the water in your laboratory, you have the capillary, this kind of the meniscus forms. So at the corner you have the adhesive force is more than the cohesive force. At the corner, at this place, cohesive force is greater than the adhesive, because the adhesive force of wall is too farther away from this, right? This is too far, these molecules are too farther away. So that's why you have the meniscus like that. Okay, you have that kind of the meniscus. So that's why look at the little bit water pulled up, right? Against the gravity. Gravity is pulling down, but against the gravity, some of the water pulled up in the corner. So the meniscus is also due to like that. So this is very, very important in the xylem and the phloem, or the fluid passing from the root to the leaves of the trees. This is the capillarity action. That much water from root to that much tall tree can climb that because of this capillarity action. That is also, there are many other factors also, but the more important is the capillarity. So this is the capillarity, the pulling of the water because of the adhesive force is greater than cohesive force, then water pulls up, okay, against the gravity, that is the capillarity. So there are two types of the meniscus, okay. Concave meniscus, let's see that water, let me make that the capillary, and the water, this is the water, water liquid have this kind of the meniscus, or it is said to be the concave meniscus. And but if you have the, similarly, if you have the mercury, let me take the mercury in this color, mercury, you will see this type of the meniscus, okay. So because in this case what is happening, you don't have the molecule here, that's why the here is adhesive is greater than cohesive. In this case mercury is heavy, right, the heavy metal. So that's why metal attraction is, it can overcome, it can too larger than the glass metal attraction, right? Silicon dioxide glass and the mercury attraction is way less than the mercury attraction. So that's why in this case what is happening, this kind of the meniscus happens. You have in that case the cohesive force is, in that case cohesive force is greater than adhesive force. In previous case adhesive force is greater than cohesive force. So in that way we have the concave and the convex type of the meniscus. Okay, so this is the capillarity. So we have already studied this, the Bontoff factors, etc. We don't need to go further about them because we have already studied those in the colligative property. So this is the capillarity, and then it is the viscosity also. We are done the chapter 6 right now, right? So in the chapter 6 I think we finished right now everything. So colligative property, capillarity and the viscosity in this video, and all others very important part of the chapter 6 are we have done in the previous video. Thank you so much for right now. In this way we have finished the chapter 6 and we will go to the chapter 7 in the next video, and see you there. Bye bye.